Now we want to compare growth rates of various functions. Let's say that you had a theory for modeling the spread of an epidemic predicts that the number of infected people T days after the start of the epidemic is given by this function. What if we wanted to know if the epidemic was going to continue to spread or die out? Well, then what we'd want to know is what would the limit of this function be as t went toward infinity? Okay, so it'd be nice to know, how does the function t squared compare to the function e to the 0.01t? So that's the basis for this last section here, is being able to compare functions that you're familiar with. Okay, so now, what we're going to look at is just certain families of functions. We're going to look at all the functions of the form m times x, where m is some positive number. Okay, now that's going to be representative of our linear functions. Then we're going to look at families of functions that are the form x to the p, where p is a positive number. This is going to be like our polynomials. Then we're going to look at x to the x, which is called our Tower function or our super exponential function. Natural log of x, our logarithms, and then log to a power of x, and then x to a power times a log of x, and then our e to the x, which will be our exponential functions. So we're going to look at these various families of functions and see what their growth rates are. Now, if you compare them, just think about what your graphs are. Okay? If you're looking at linear functions, the pink ones down here are all of our linear functions. These are the graphs of y equal to 100x, y equal 200x, y equal 300x, and y equal 400x. Now, they don't look like they're rising that quickly, but that's only because we're comparing them in this graph to y equal x to the power. So the blue graphs are y equal x to the third. Okay, that would be, this one right here would be y equal x to the third. And that is so much larger, it's growing so much faster than even y equal 400x is, which would be this top one. So when you look at them relative to each other, you see that some groups of functions grow much quicker than the others. So our linear functions grow much slower than our exponential function, our polynomial functions. So the polynomials grow faster than the linear functions. Now look at the exponential. Exponentials where the variable is in the exponent. So like e to the x and a number to the x power. These are the graphs of y equal 2.25 to the x power, y equal 2 to the x, and 3 to the x. Okay, so if this is our y equal 2 to the x, y equal 3 to the x would be the one on the inside here. These are so much faster growing than just x to a number. So let's see, this would be x squared, and that doesn't look much like a parabola. But this bottom one here, that just because of the scale that we're using, this would be y equal to x squared, and this one up here would be y equal to x cubed. So when the variable is the base with the number for the exponent, those functions, these are your polynomials, grow much slower than your exponential functions do. So since our polynomials grew faster than our linear functions, and our polynomials grow slower than our exponential, then we can see then that obviously the exponentials are going to grow much, much faster than our linear functions. So that's the idea here between, comparing the growth rates. Okay, so now what this theorem says, suppose f and g are functions, and both of them have limits that are going to infinity. If you graph the line y equal to 10x, as x gets larger and larger, the y value is going toward infinity. But how fast is it going toward infinity? If you look at the graph of y equal x to the third power, it's going to infinity much faster. Or 2 to the x. It's going to be even going faster. So how do we know there's a significant difference in how fast each is growing? So we're going to assume that both of these functions have limits that are infinity. Now, what it means to say that f grows faster than g means that as x goes to infinity, the limit of g over f See, f is growing faster. So if f is on the bottom and it's growing faster, then g is smaller than what the f is. So if the limit of g over f is 0, then we say that f is growing faster than g, or g is growing slower than f. Okay? We can also look at it is if f is the faster growing and it's in the numerator, then you would assume that this fraction then would be going toward infinity. So what we're going to look at is we're going to look at a ratio. If we're trying to compare f and g and see which grows faster, we're going to look at that ratio and see, does that ratio go to 0? If it does, that means the one on the bottom is growing faster. If that ratio goes to infinity, that means the one on top is growing faster. Okay? Now, if you don't get 0 or infinity, you get some number in between, then what we say is that f and g have comparable growth rates. So maybe one of them is just twice as fast as the other, just some multiple of the other, but not a whole nother factor larger. So that's what we're going to do. We want to compare growth rates. We're going to compare the ratio and find the limit of it. If the limit's 0, the one on the bottom grows faster. If the limit's infinity, the top one grows faster. If it's a constant, then they are comparable growing. So something like 100x and 200x. That growth rate would be a constant, and they would grow they're comparable. Okay, so now, just in general, if we look at natural log of x and x to the p, I want to see which one grows fastest. Let's look at the limit. It doesn't matter which way you do it. I'm going to look at the limit of x to the p over natural log of x. It doesn't matter which is on top. And we're going to look at x approaching infinity. Okay, so now if I were trying to evaluate, I'd have a large number to the p power, so the top would be approaching infinity. The bottom is also approaching infinity. This is an infinity over an infinity indeterminate form. So L'Hopital's rule says I can rewrite this as the limit of p times x to the p minus 1, the derivative of the top, over the derivative of the bottom. So now I can simplify that. That's the limit. Now when I invert and multiply, this is just going to be p times x to the p minus 1 times another x, which will just be the limit of p x to the p. Now as x approaches infinity, this clearly approaches infinity, so the limit would be infinity. So what we just learned was if we looked at this ratio, the limit was infinity. So which grows faster? Well, that would mean that the top one, this grows faster than the natural log of x. Now, the way we're going to do that, we're not going to say that natural log of x is less than x to the p. What we're going to do is we're going to use that notation and put a double less than to mean grows faster. Not just smaller, but it grows, significantly faster. X to the p grows significantly faster than natural log of x. Okay, and what that means is that if I take the ratio ln of x over x to the p, it's going to be 0, since the x to the p grows faster. Okay, now the next one here, we're going to key off of the one that we just found. Okay, so I'm going to start with the ratio. I want the limit of natural log to the qth power of x over x to the p. Now, I have a q power of natural log on the top. So what I'm going to do is I'm going to rewrite this. I'm going to make this to the qth power so that I'm going to have natural log of x on the top. And then now the bottom, remember your rule for exponents, if you have x to a power to another power, you'd multiply them, the exponent. So this will be x to the p over q. So just algebraically, those are equivalent. But now, look at the problem before. We know natural log of x grows more slowly than x to a power. Any power. It doesn't matter what that number was. Natural log of x, as x is going to infinity, natural log of x grows slower. So this is the same thing as, I'm going to put that power q outside of all of this. This is the limit of natural log of x over x to some number And this limit, since we know natural log of x grows more slowly than x to a power, that means that this limit would be 0. Okay, so now which grows faster? If the limit of this ratio is 0, that means the one on the bottom grows faster. So natural log to the qth power grows more slowly than x to a power. Okay? Okay, so now x to the p and e to the x. Now notice we're building a table down here at the bottom. This notation means that g grows faster than f. Okay? So now we've just shown that the natural log of x to a power grows slower than x to a power. Okay? And now we're looking at x to the p and e to the x. Okay, so now let's look. Let's just look at a ratio. We're going to have x to the p over e to the x. Now, if I evaluate, I'm going to have infinity over infinity form, so I can use L'Hopital's rule. This will be p x to the p minus 1 over e to the x. Now, what's going to happen is, p is a positive real number to start with. So as I continue decreasing this value in the numerator by taking derivatives, notice again, I'm going to have an infinity over infinity form. So I'm going to continue reducing the power of x in the numerator so that the numerator is getting smaller, but the e to the x stays the same each time. So just intuitively, it seems like the bottom's being reduced and the bottom's staying large. So it seems like this is going towards 0. But let me show you a little substitution, a little trick to actually see it more clearly with our previous results. I'm going to let the x here equal to another variable. I'm making a change of variables. I'm going to let x be natural log of t. So this is going to become the limit of natural log of t to the p power. On the bottom, I'm going to have e to the natural log of t. Now notice as x approaches infinity, then that means t is going to also have to approach infinity. So if I'm changing my variables, I know that the t is also going to be approaching infinity. Now, simplifying this, I have the natural log to the p power of t, and on the bottom now I'm just going to have a t, and I'm letting t go to infinity. Now, we just showed on the previous problem that natural log to the pth power of some variable grew more slowly than t to the qth power, I believe. Okay, x to the p just had to have two numbers. It doesn't matter what they are. Okay, so I know the natural log of a variable grows more slowly than that variable raised to a power. So that means that this grows more slowly than this one, because that's t to the first, which means that this limit approaches 0. So what that means then is that comparing these two, if that limit is 0, that means x to the p grows more slowly than e to the x. Okay, so here's our polynomial functions, and here's our exponential functions. So they're in a totally different class of growth rate. Okay, and so that fills in a few more down here. We have the comparison of the polynomial functions and the exponential functions here. Okay, now you're going to be using this table in a Calculus 2 class. It's comparing some growth rates, and just by using L'Hopital's rule, you can establish these. But if you know in advance that certain types of functions grow more quickly or more slowly than others, it just saves you some time. So when you start doing infinite series, this could be useful. So now I want to work a couple problems and just show you how you might incorporate this. Let's say we were comparing natural log of x to the 20th power and natural log of x. Okay? In the growth rate, I would look for each of these in the table. Okay? Now, natural log of x to the 20th, though, that's the same thing as just 20 natural log of x. So we're comparing 20 natural log of x to natural log of x. So if I wanted to find the limit, which of those grows more quickly, I'm going to put 20 natural log of x over natural log of x. And the natural log of x's would cancel. That's just the limit of 20, which we know is just 20. Well, these two grow or comparable, have comparable growth rates. So just take the ratio of the two and see if you come up with 0, infinity, or a constant. Okay, x to the 20th and 1.01. Well, we saw that x to the p grows more slowly than e to the x. And in the table, we even generalized it to say that x to the p grows more slowly than just b to the x. It didn't matter what kind of base we had. So that would mean then that the x to the 20th grows more slowly than even 1.01 to the x, because in the table, the b just needed to be bigger than 1, and 1.01 is. So that means that this one grows more quickly. So x to the 20th grows more slowly than 1.01 to the x. So just look at the forms. This is the same as an x to the p, which is in your table, and this one is in the table, and this is the order that they're in. So if we wanted the limit of x to the 20th over 1.01 to the x as x goes to infinity, well, the one that grows faster is on the bottom, so this limit should be 0. Okay, now x to the x and x over 2 to the x. Okay, if I want to compare those two, I'm just going to look at the limit of a ratio. So the limit of, let's say, x over 2 to the x power and x to the x. Now, what I'm going to notice is I have the same exponent, so I'm going to go ahead and simplify by combining these two. That's x over 2 over x, all to the x power. And then when I invert and multiply, that's just going to give me the limit of 1/2 to the x power. And in all these, x is going to infinity. Well, the limit of 1/2 to the x goes to infinity. So if the limit's infinity, go back to what the ratio that you put together was. These were the two functions we were comparing, and if we get infinity, that means the one on the top grows faster than the one on the bottom. Wait a minute. If x goes to infinity, that didn't make sense because that top one wasn't it's half of the other one's base. This is a fraction. 1/2 to the x. As x gets larger and larger, this is the same thing as the limit of 1 over 2 to the x. Now, as x gets larger and larger, the bottom's going toward infinity, but the top's 1. That limit's going to be 0. And that makes much more sense. So, if we were comparing these two, we got a limit of 0 for this quotient, and that means the one on bottom grows more quickly than the one on the top. So this one I was expecting either that to be the case or maybe even the same growth rate, because all we did was half the base. But it does make a considerable difference in how fast they're growing.